We'll be beginning our look at integration. And so this is going to kind of develop exactly what it means to do that. You've seen symbols and we've talked a little bit. This will actually kind of solidify that. So we're going to look at the relationship between a rate of change function and the area between the derivative graph and the x-axis. And so we're going to look at this real simplistic example, the way we're going to do it, and then we'll talk about how we need calculus to do it if we don't have nice horizontal lines like we're going to have. Okay? So this is an example that's talking about the tropical cyclone Imelda that brought more than 40 inches of rainfall over a 72-hour period in southeast Texas in September of 2019. So the scenario is, in order to avoid flood water entering your home, you run a pump that can remove water at the rate of 500 gallons per hour for the first 8 hours. As the storm gets more, okay, you decide to get another pump, and for the next 16 hours, if using both pumps, you can remove 900 gallons per hour. Okay, so first thing we're going to do is we're going to basically draw a graph that models this situation. Okay, so we have this grid here. And so we know that we're going to have, this is going to be time across the horizontal part in hours. Always make sure you're careful about that because, you know, hours, minutes, seconds, days, what we don't know, can't just say time. And then the other part that we will be doing is a function, and we're going to name it g of t because we have gallons of water over time. So we'll say this is our g of t function, and this is our gallons of storm water. Okay. So let's see how we would graph this. Okay. So if we are removing, so if we are doing 500, looking back at the problem, which you can see on your paper there, we're removing 500 gallons per hour for 8 hours. So that means that we are a constant here of 500 gallons each hour for the first 8 hours. So this is how much we're removing. This is how many gallons of water we're removing per hour. Okay, and then at 8 hours we get another pump, and now we can get 900 gallons out. So now it switches up to here, and for the next 16 hours, all the way there to 24 hours, we're going to be at this rate. So that's the graph that models that. Okay, so now let's go look at this question. So this question is talking about when we talk about area under a curve, it represents the area between the graph and the horizontal axis. So find the area of the graph from 0 to 8 hours, and what does that mean? So if we find the area of underneath the graph here, for the first 8 hours, you're going to have 8 times the 500, which is going to be 4,000. And what is that going to be? Well, it's 8 hours times 500 gallons of water, so that's going to be 4,000 gallons of water. So what it means is, so we know the answer, which we wrote on the graph, but we'll just write it right here. 500 times 8, of course, would be that rectangular area, which is 4,000. So what does it represent in context of this problem? Well, it represents a total of 4,000 gallons of water and say stormwater. Remember how we want to write everything exactly like the problem. So they called it stormwater. So let's say stormwater was removed during the first 8 hours. Okay, so that's what it means, and we probably should go ahead and say during, this storm, okay? All right, so that's what it means. So we know that each hour we got 500 gallons out, so 500 times 8, 4,000. So this is the total amount of water that was removed over the first 8 hours. Very important that we always give everything in context and over time intervals, and we've talked about that before. Okay, then it says find the total area of the graph for the entire 24 hours and interpret that. So if we go to this second part, we also have a rectangle here. And so the area underneath this curve is very simple. It's going to be 16 times 900 because the width of the interval is 16 and there's 900 gallons each hour being removed. So this is going to be 14,400 in this area. So that means in the first 24-hour period, we would have 4,000 plus 14,400 or 18,400. And again, what does it mean? So explain in context. Well, in context in the problem, we would say in 24 hours of pumping storm water during Imelda, a total of 18,400 gallons of storm water was pumped out. Okay, or removed, or whatever you want to say. Okay, so that's the context of the problem. Well, that problem's super easy and very easy to see what's going on because you have just a nice rectangle and it's very constant. Every hour you're getting so many gallons out, so it's really easy to figure out. Well, most of the time that's not the situation. Okay, usually things vary, so we don't have a nice constant function. We have some kind of function that varies. And so we have to figure out how are we going to do this same thing. Okay, so if it's not constant, we're going to basically take the idea like what we did with the tangent line problem. So with the tangent lines, remember, we took secant lines and we just kept moving them closer and closer, the points closer and closer together. So we took the limit as the distance between them, the h went to 0 in order for us to get the tangent line. So we used a limiting process. Well, the same kind of thing, that's the derivative. The same second really important problem is finding area under a curve. Okay, so two problems, derivatives and integration. Those are the two things. And you will hear people say differential calculus and integral calculus, and that's basically what that, means. Okay? So let's look at more things. So the idea will be, actually, you can come back and look at this. We're going to look at the example, and then you can go back and look at that. So I should have mentioned, so I'm going to mention now that it would be a good idea for you to have some colored pencils out for in a minute for some questions we're going to do, and then also I would have your calculator out. So if you don't have those two things, you might just pause the video, go grab your calculator and some colored pencils. The calculator is what we need right now. So I'm going to go ahead and let the calculator app start opening while we read this question. So we have this 30-gallon aquarium. We're filling the water, and So we're filling the water at this function. Okay, so this function RT, etc. Again, it doesn't matter. Don't spend a lot of time worrying about that. That's what models how we're filling the water. T is in minutes. Always a good idea to sort of, oh, I'll get back to that. A good idea to underline. T is in minutes. And RT is in gallons per minute. Okay? So it's important to remember that because our units, so we get our units right. Okay, we want to find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and have a height of RT. So these have already been drawn on there. So you can see the function is drawn there, and that's not what we're going to use the calculator for, but that you could draw it on your calculator and you could see that function. But you know, later, obviously, we're going to learn easier ways to do all these things. This is the concept that makes it important so that I know when to apply things and how to work on stuff. So what we're going to do is we're going to approximate the volume of water. So here's the important thing to remember. If this is gallons per minute, and I want gallons, because I want to know how much water is in the tank, so I want gallons, then that means I need to integrate it. I need to find this area underneath. Because if I find the area underneath, I will get gallons, okay, just like what we did in the last example. So what we're needing to do then is find the area of these 5 rectangles, and we're going to make a little table to do that, and then we're going to use our calculator. So make sure that you have your, again, have your calculator ready, and make sure it's in radians. If you're in degrees, this will not work, so be sure you're in radians. I'm going to scoot it over here, and then we're going to, I think we can fit it here on the side. So we're basically going to make a little table to kind of write down our values. Okay, so we have T, which is our time. So we're going to do this for, well, I'll show you in a second. And then we have R of T, which is our function. And so what we're going to do is we're going to need to find the area of each of these rectangles. Well, if we look, each rectangle is 1 unit wide. So if we want to figure out the area under the rectangle, or the area of the rectangle, I'm simply going to take 1, that's the width, times the height. Well, the height is the function evaluated at 1. Okay? So since every rectangle is just going to be 1, this width, which is 1 times the height, then I don't really need to, I just need to find the heights and add them up in this case because the widths are all 1. So I'm going to start with T equals 1, and that's this endpoint. Now, I want you to notice something. These rectangles have all been drawn using the right endpoint of the rectangle as the height. That's important in a minute because we're going to talk about right and left and other things that we could do. So you notice that all of them are drawn where the rectangle's height goes on the right endpoint of the interval that we're dealing with. So here's this interval from 0 to 1. Okay, so since what we're going to do is we're going to have to find this value, and we're going to have to find this value, and we're going to have to find this value, and we're going to have to find this value of the function and this value, well, it totally makes sense for me to store this function. So I could just plug those numbers in, okay? So we need to do that. So let's go ahead and do that. So you remember you need to go to a calculator page. And then you want to type in your function, and your function is 6 sine of pi over 8 t Now remember, we're always going to use X, right? So that we can graph things and do whatever we want. And then get out of your inside of that parentheses and then control of var to store it. And we might as well just call it R of t, because remember, we can just start a new problem. Oh, we'll call it R of x though, right? Remember, always use X. Life is easier if you do that until we get to parametric and polar, but we'll know we want to change it for those reasons. So I just say store, I'm done. Now I'm going to fill in my table. So I need to know what is that value at 1. So I'm simply going to do now R of 1 and hit enter. And then of course I want decimals for these because I'm using a calculator. So I get 2.296, remember 3 decimal places. And then I want to do the t is 2. Its height is right here. Here's the height. The width again is 1. So the area of that rectangle is just going to be the height times 1. So just the height. So now I'm going to do R of 2. So I just do R of 2. And remember, if you put a decimal point on the number there and then hit enter, it'll automatically give you the decimal. You just have to put 1 decimal point in and you'll get that. So that's 4.242 or 243. It doesn't matter. Remember, round or truncate. And then we'll just keep going. So we'll do R of 3, R of 4, and R of 5. And remember to stick that decimal point and then hit enter. So we get, for that one, for 3, we get 5.543. And then for 4, again, just stick a decimal point there. We get 6. So that one was nice. It comes out 6, at least to the number of decimal places that it's keeping. And then R of 5 is our last one. Again, sticking that decimal point in so it just goes directly to our decimal answer. So when we plug in 5, we get 5.543. So these numbers here are all of the heights of all the rectangles. And again, to find the area of all those colored rectangles, I would need to add up the area of each rectangle. And that would give me the approximate area, okay, the approximate area under the curve from here to here. That's what that's going to give me. It's not exact, of course, because my rectangles have gaps, but it's going to give me approximately the area under the curve there. Okay, so I would simply add all of those up, and I'm not going to take the time to do that. You can do that yourself, and you get about 23.625. if I add all of those up. Then we have to decide, okay, what does that mean? So find the volume, or find the volume of water in the tank after 5 minutes. So we've got to actually say what we found. So what we found is after 5 minutes, and again, always a time interval. Always give over, or not necessarily time, but over the interval. So what we found is over this interval. After 5 minutes, the aquarium has about 23.625 gallons in the tank. Okay, so always in context of the problem and always with units and over whatever interval. Okay, so we're saying in the first 5 minutes or after 5 minutes, the aquarium has about this many gallons in the tank. Okay, so if we wanted a better approximation, so if we look back at this, we can see that clearly there's places where we have extra area that we don't need, right? This is all extra. It goes above that curve. And then we also have a little tiny place here where we have a gap. Okay, so right here we're actually missing some stuff. We have a gap there. Well, so we know our answer is not right, okay? But you should be able to imagine pretty easily if we just made smaller rectangles, we would have less extra stuff and less missing gaps. And if we just kept making smaller and smaller and smaller rectangles, if they got small enough, as they went to the size of the width being 0 or the number of rectangles going to infinity, then we would have exactly that curve underneath. And so that's the idea. That's the same idea that we're going to have for doing that. So basically, we're going to take the limit, and we're going to look at that too, but we would get the exact amount, okay? And then this is how we would write this problem. We would say that we are integrating from 0 to 5 of r of t dt. So if we wanted, again, this purple area, this exact area from here to here, so we wanted exactly this area without the extra stuff and without the missing things, that is represented by the integral from 0 to 5 of r of t dt, okay? So we're going to learn how to approximate those answers and then see how that translates into getting to be able to do exact answers. Okay, so we call this a left endpoint. I don't like to call it a lower sum, so don't do that. It's a left endpoint inscribed rectangles, okay? So if you have your function and you're trying to draw rectangles, if it's a left approximation, left endpoint, it just means that here's your intervals. Okay, we're going from here to here, and we've divided it into these intervals. So we're using the left endpoint, drawing a rectangle. Well, there's nothing there because that happens to be 0. Here's the left endpoint, and then we draw our rectangle. Here's a left endpoint of the next interval, start, and we draw the rectangle. Left endpoint, draw the rectangle. Okay, so this is what we call a left rectangular approximation method, left endpoint, left Riemann sum. There's going to be lots of names, okay? If we do the right hand one, we just do the same thing, but we have our interval here, and our first interval goes from here to here. So we take the right endpoint and then draw a rectangle. Right endpoint, draw the rectangle. Right endpoint, right endpoint. Okay, so we call that a right rectangular approximation, or just the right endpoint or right Riemann sum. Okay, and it's only an over approximation if the function is turned a certain way. So that's why I don't like to say that now. We can also do something called a midpoint approximation. So again, we have our same interval. We're going to divide into 4 rectangles, but instead of using one of the ends, we're simply going to use the midpoint. Okay, so I'm going to take the midpoint of the interval, go to the function, and then draw my rectangle. And I just keep doing that. Midpoint of the interval, draw the rectangle. Midpoint of the interval is the height, and then draw your rectangle. Now you can see that that ought to be a little better approximation because you're going to have always a little piece that's out and a little piece that's in. I mean, no matter how the shape of the graph is, you'll have some over and some under. So it can be a better approximation. And we also, basically, we call these Riemann sums, okay? So that's just a name that we're going to use. So this is the nice formal definition. So the formal definition says, forget about A over B partitioned into subintervals and all that. This is simply delta x is the same thing it means in many, many times that we talk about it. This is it represents a x, something in the x direction. So this is the width of the interval. Okay, so I decide I'm going to make rectangles and I'm going to make them however wide. Well, that's the width. F of CK. Well, C is the right or left or midpoint. It's wherever you're deciding to do, whatever you decide to do. That's this point. If you take F of that, that's the height of the rectangle. So essentially, this thing is the height, and this is the width of your rectangles. Well, you take the height times the width, and you get one of your rectangles. Well, this means summation. K equals 1 to n means first rectangle, second rectangle, third, fourth, fifth, like when we did the 5 underneath the curve. So however many, n is just however many rectangles. Okay, that's how many you decide to have. So if we add them all up, we'll get an approximate area, like the example with the 5 colored rectangles, and we got an approximate area under that curve. But if we take the limit as n goes to infinity, that means we have an infinite number of rectangles, which means they, by that logic, have to be smaller. And if I'm going to infinity, that means technically the width of each of those becomes not any width, okay, becomes no width. And so you will get the exact area under the curve from A to B. Now, it's only area under the graph if the graph is above the x-axis. So we'll talk about how to be careful about that. So this is area between the curve and the x-axis, okay? If it's underneath, it's going to be negative, and we'll talk about that in a second. The integral itself is not always area, okay? So basically, here's kind of some steps. You're just going to draw a graph, but we're just going to do that, okay? So let's start with example 3. So here's where a colored pencil might be helpful. This one you don't really need colored pencil, just whatever you're using. So we want to approximate the area under the graph of f of x equals 1/2 x plus 1 from 0 to 5. And we're going to use geometry. Well, even though this seems really silly, because that obviously should be really easy, we're actually going to use geometry sometimes to answer these questions. So we do need to practice that. So we're going from 0 to 5. Well, because this is a line, we end up with an exact shape that I know exactly how to find the area, and that is a trapezoid. And so we can actually not just approximate the area, we can actually find the area. And the area of a trapezoid is 1/2 the height times base 1 plus base 2. Now, when you look at this, remember that the bases are the parallel parts, okay? So these are the parallel sides, okay? They're bases. So our trapezoid is technically, like you might think of it, as sideways, because the bases would actually be this length and this length. Those would be the bases. The height would be right here, because it's flat. So the height of this would be 5. Base 1's length is 1, and base 2 is, we'll call that 3.5 is what it looks like. Now, how could I find that out exactly? Well, plug 5 in right here, right? So f of 5 is going to be 5/2 plus 1, but 1 is 2/2. We get 7/2. So we know it is, in fact, 7/2. So if I want to find this answer, this one is pretty simple. It's 1/2 the height. Again, this is the height of this trapezoid. So 5 times base 1, which is this length here, which is 1, plus this base, which is 7/2 or 3.5. And then I would just find my area here. I would encourage you to really work with the fractions just because it's, good practice. So 1/2 times 5 is 5/2. 1 plus 7/2, that would be 2/2 plus 7/2, 9/2. So we get 45/4. And then we don't have any units here, so let's just call it units squared. It's just so we're in the habit of always putting units there, okay? And that would be my answer. So in this case, I have an equal sign because this is in fact equal. That wasn't a curvy shape on the top, it was actually a line. So I can find the answer. Now, these will be different. These are going to end up being not exact. So what it's going to have you do is you're going to draw on this graph. We're going to do A and B and find the left-hand sum and the right-hand sum, and we're going to shade them with different colors. So that's why I was saying this is where you need your colored pencils. So for the left-hand sum, we're going to do the rectangles in blue, and we're going to calculate the area from 0 to 6, because we're going to let delta x equal 2, which means I want my width of my rectangles to be 2 wide. So here's one, here's the second one, and here's the third. Okay, so there's my rectangles. So we're going to do the left-hand sum. So left-hand means here on the left, okay, I'm going to put a dot. And then I'm going to draw a rectangle all the way over to the right-hand side, and then I'm going to draw it down. Now you're using colored pencils, so draw really lightly, but just draw a blue one. And then very lightly shade blue. I'm just going to kind of put some cross hatches because I can't do light very easily. So you can just lightly shade that in. It's not art class, don't spend an hour on it. Okay, then I'm going to go to my next interval. So my next interval is 2 to 4. So I go to the left-hand side, which is right here, and then I'm going to make a rectangle that goes over to the right-hand side and down, and then I'm going to lightly shade in that area. And then my last interval goes from 4 to 6. So I'm going to go from 4 over to 6, and then I'm going to lightly shade in again. Okay, so this would be the rectangles that represent that left-hand sum. So how would we find that approximation? Well, you have 3 rectangles, so we would add them up. Okay, so my area would be approximately now, not exact, because now I'm estimating it by adding up these rectangles. Now technically the left-hand sum would give me the answer, so I guess we could, instead of saying area equals, let's just call it the left-hand and equals. So this is the left-hand sum, and we did those 3 rectangles. Well, the nice thing about the way we did it is because we decided to divide them evenly, and you do not have to, but it's easy in this case because I made all of their heights equal. They're all height, or the width of every rectangle is 2. So I could put 2 times the function value, 2 times the value, 2 times the value, but I could also just factor out the 2. So the first rectangle would be 2 times the height. Well, the height is right here. That's 8. That's the left-hand's function value. Plus, then you would have another 2, so think distribute, times this height. That's 7. That goes to 7, plus this height right here, 2 is still the width again, and this height is 5. So my left-hand sum is going to be 40 if you add those up. Now, is that over or under the real area? Well, you can see by looking at the picture, clearly that's over, right? Because you got pieces of those rectangles that are all outside of the graph. So that's important. Now, next thing we do, we're going to use red, and we're going to draw all the right-hand ones, and we're going to find that one. So if we do the right hand of each interval, if this is my interval again, that's my first interval, so that means I put a dot here, and I go this way. That's the right side of my rectangle, and then I shade. And then I do it again. I go to the next interval, I take the right-hand side where it hits the graph, and I draw my rectangle. So that's here. And then I go to this last interval. The right-hand side is 6. So I put my dot, and I draw this rectangle right there. So the red represents the right-hand sum, okay? So to do the right-hand sum, we're going to, again, have a width of 2 for every one of them. So all I have to do is take it times each height. So the first height is 7 plus the next height, which is 5, plus the last height, which is 1. So we're going to get 13 times 2, or 26. Now the next question, C, says which one overestimates and which one underestimates. Well, clearly in this case, the left-hand sum overestimated and the right-hand sum underestimated. Okay? Then it says do the same thing again with this function. Okay, so we're going to do the same thing. So we're going to draw first the blue ones. We're going to do the left hand and see what we get. So we're going to take our interval from here to here, because that's where our points are and our start and finish. And we're going to, it says let delta x equal 0.5. So there's 0.5, there's another 0.5, and that's the last 0.5. So again, it's even. It doesn't have to be, but it is. So that does help. So now I take my left endpoint, so that's this left side, I put a dot. And then I'm going to draw a rectangle. And then I'm going to shade. That's my first one on the left-hand side. Then on the next one, I go again up to the graph on the left side of the interval and then draw a rectangle. And then here's the next one. And then I'm going to go on the left-hand side again, put a dot, and I'm going to draw a rectangle. So this time the left-hand side clearly underestimates. Okay, so looking at the shapes of those two graphs, that'll help you figure all that out. So basically we have 1/2. Remember, fractions are actually easier. So the width of every rectangle is 1/2, and then I just have to add up the 3 heights, because I'm basically, again, distributing out that height for each one of them. And so I'm going to get 11/2 or 5.5. It depends on how you want to do it. So the right hand, we're going to do in red, just like we did the last one. So again, the right hand of the first interval will be here. So I'll draw my rectangle, and it will be out here. My rectangle has to have the height at the right side. Right side again. So up here is where we draw. And then we fill that in. And then right side here. So again, this is where we draw. And then there's my interval. So again, this time we actually get an overestimate. But still height, or the width is 1/2, and then the heights are just the right side, you know, of the rectangle. So we'll have 4 plus 6 plus 7, which is 17/2, or if you want to write 8.5, you can. Okay, so last thing we're going to do, and then we'll save the last example to do in class. So last thing we're going to do is kind of look at this. What do you think is going to happen? So looking, you can see your 2 graphs right there on your paper. So if you look, forget concave up and down isn't actually going to end up mattering. What's going to matter is increasing and decreasing for this. So the bottom function is increasing. So that was the bottom one of the 2 that are above you, above this table. So when we did the left-hand approximation, we got an underestimate, right? It was under on the increasing function. All my blue rectangles are underneath. And the right-hand one was over. On the top function, that was a decreasing function, we ended up with the left-hand one. If you look at your blue boxes, those were all over. So this was an overestimate. If we look at the right-hand ones, we get under. And you'll find that does not make any difference. The answers would be the same no matter what the concavity, because it isn't the concavity that matters. What matters is increasing or decreasing, okay? Because if it was increasing but it was concave up, I still, if I drew my my left hand endpoints, I would still always get left hand, and then I would go down, and then I would be on the left side and go down, and I would still be under. It doesn't matter whether it's concave up or concave down. So increasing and decreasing are what tell us whether we're going to be under or over. And so what I like to do, if the question asks me if this is an under or over approximation, then I would, if the function's increasing, then I would sort of draw my boxes and say, oh, they're all underneath, you know, or they're all over, depending on what you're doing. So that's it for this video. We will do the remaining portion of our notes in class as a kind of review and to organize that information.